Okay, we will continue with Annex 86. I want to invite Professor Laverge from Ghent University in Belgium, and he's operating agent of Annex 86, and this is about energy efficient smart IQ management in residential buildings.
Yes. Okay, so dear chairs, thank you for the introduction. Hello, everyone. I'm here to give an introduction to Annex 86 as a lead up to the presentation, the next presentation by Benjamin Jones about one of the areas that we are working on in the Annex. So I'll just give a general introduction about what the Annex is about. So as Hilde introduced, it's called Energy Efficient IAQ Management in Residential Buildings. So to give a bit of context about the Annex, as we've heard many times already today, and probably we all know, indoor air quality is a very important constraint when we are thinking about improving energy efficiency or optimization of energy efficiency in buildings. However, and this is also already mentioned in previous presentations, so far we do not have a good consensus on how to rate indoor air quality, how to assess indoor air quality, to then make decisions in terms of improvement of energy efficiency based on that. And so this is the general context that Annex 86 is trying to work in, to come to a framework that allows to make the IAQ assessment to then make decisions for improving energy efficiency. We are focusing on residential buildings for multiple reasons, namely that, as Ian mentioned earlier, typically we have much simpler systems in residential buildings. And on the other hand, the challenge towards retrofitting and improving energy performance is biggest in residential buildings. We have most floor area in residential buildings. The share in total energy use and emissions is the biggest in residential buildings. And also the type of use is much more diverse and varying in residential buildings. So this is why we are focusing on residential buildings. And for those buildings, we have a number of different aims in the Annex that we are trying to work on. Let's continue. To achieve those aims, we divided the work in our Annex in 6 subtasks, where subtask 1 and 2 are focusing on developing methods that will allow to assess the indoor air quality in buildings and compare it across different buildings, where subtask 1 focuses on the development of a metric, specifically further development of a health-based metric to assess indoor air quality. And then subtask 2 tries to provide the input information that is needed to calculate that metric. Then we have 2 subtasks that focus on the application of those metrics and assessment methods in different types of technologies that can improve indoor air quality. We just heard about air cleaners, which has its own separate annex. So we're not focusing on that in Annex 86. We focus on the one side, smart materials. So you could say passive air cleaning technologies, where the materials in the space contribute to the improvement of indoor air quality. And then in subtask 4, we focus on smart ventilation. So how improving the operation of ventilation system through the use of demand controlled ventilation, sensor technology, and control of the system over time can contribute to improving indoor air quality with the same amount of energy use. And then we have 2 subtasks that focus more on opportunities and outreach, which I will not discuss further. What I want to highlight in this talk is the applications of what we're trying to do. And basically there are 3 types of applications where you could use a performance assessment method. The first one is a relatively simple one where you're just comparing different buildings or different rooms or different situations in buildings, one to the other, and trying to decide which one is better than the other. This type of application was the focus of our previous annex, Annex 68. And you see a result here. So in that annex, there were a number of indicators that were developed that were then shown in these types of graphs, where you clearly see the performance of a building for each of these indicators, and then you can compare 1 or 2 or 3 results for different buildings and try to decide which performs best. However, this requires a lot of information about the indoor air quality that you expect in those buildings, and can best be used if you have measurement results for different spaces. In this annex, we try to focus on 2 different cases. I would call it an engineering case and a regulatory case, where in the engineering case, basically as an engineer, we are considering different options for systems for a specific space. And we're trying to decide before we build it, what is going to be the best option to take. And for that, we cannot rely, or it's difficult to rely on measurements. You need a simulation that will give you a good prediction of what you can expect as a result. And then the last case, or the second case that we are focusing on is if you're a policymaker, for example, drafting standards, as we heard from Ian earlier, you're trying to decide which guidelines or which requirements will have the biggest benefit compared to the investment that needs to be made. And there, what you really want to do is have that same kind of predictive power as in the engineering case, but now apply it to generic buildings that will represent as much as possible the expected conditions in buildings across the building stock. And so, sorry, this is what we are trying to achieve or to add to the existing literature, providing tools that address these 2 issues. To get there, based on the results from Annex 68, there are a number of things that are methodological issues that still need to be addressed, or that we're working on. One of it is that most of the available indicators for indoor air quality focus on long-term effects, but on the other hand, smart ventilation controls, things that modulate the operation of the ventilation system, also have potential short-term effects. It was already mentioned, you can have very high peak concentrations, and we also need good indicators for that. And so the graph you're seeing is a concentration that was simulated for a specific space, and then the application of different reference levels that we found in literature that could be used as a way to limit short-term effects. These short-term effects also apply to the concept of resilience of a ventilation system. So not only deliberate control strategies that change the exposure over time, but also unexpected events can have an effect on the indoor air quality. And we want to check whether the chosen solution will be more or less robust against peak exposures due to unexpected events such as power failures or haze events, things like that. Another methodological issue is non-long-term health effects, so acute effects that could be irritations, typically called sick building syndrome. What's the I struggle to find the word, but symptoms that are caused by acute exposures that lead to irritations such as dry eyes, headaches, and things like that, which have an impact, but are difficult to quantify based on health outcomes, which is the focus of what Ben will discuss afterwards. And so we also try to capture those by accounting for the indirect costs that are associated with the loss of productivity due to lack of concentration or absenteeism that is expected based on acute exposures and the sick building syndrome symptoms that are associated with that. And as you can see in this graph, for an average ventilation rate of about 10 liters per person in different conditions, here we expect that the total annual cost per person associated with that would be around 6,000 euros. So negligible cost associated with not providing optimal indoor air quality. And then a last methodological issue that does relate more to the long-term aspects is what is actually an acceptable level of harm that could be caused by a system or a choice for a system. And basically there are two approaches that can be taken. One is basing the acceptable level of harm on what is now deemed acceptable based on existing standards. So for example, the current standards in 62.1 or 62.2 provide a certain level of protection, and we think that is okay. Or it could be more based on an absolute threshold, like we accept an increase of deaths related to exposure of 1 in a million, which is a threshold that is often used, for example, to determine acceptable cancer risks. And this is some work by Klaas de Jonge that looks at these different options and looks at the expected benefit from different systems based on which reference you choose. So to wrap up and go to our conclusions, we're trying to provide a framework that allows to make this assessment, for which we take into account all of the different chemical and physical processes that determine the concentrations in a space. We're trying to fill in missing information, like, for example, missing those response curves. And to get to that information, we're focusing on providing input data for models. And a very important activity in our subtask 2 is collecting existing measurement information from which we're trying to derive average source strength in buildings for different pollutants. So if you have measurement information from measurement campaigns in residential buildings, that would be very helpful if you could contribute to this work. And for that, you can contact me. So I'll skip this and conclude that we are trying to provide a ecology of methods that allow to apply rating methods in the different conditions that I described. And I would like to thank AIVC for partnering with us to help us collect your input for that. Thank you very much.
Oh, thank you very much. Unfortunately, we have not. Okay. Next speaker is